Your AI monitoring system says latency is critical. Users are complaining. Dashboards are flashing red. But what if the network isn't overloaded? What if it is misconfigured? Today, we'll break down how AI detected high latency and how one engineer uncovered a hidden QoS mistake. Modern enterprise networks rely heavily on AI-driven monitoring tools. These systems continuously analyze traffic patterns, baseline performance, and detect anomalies in real time, often faster than any engineer manually reviewing logs. In this scenario, the AI dashboard triggered a high latency alert across multiple business-critical applications. Response times were climbing beyond normal thresholds, and users began reporting delays in voice calls and cloud services. Now, here's why many teams make a mistake. High latency does not automatically mean congestion. Latency simply means delay. The time it takes for packets to travel from source to destination and back. And delay can be introduced at multiple layers: queuing, processing, routing decisions, or policy enforcement. The AI detected the symptom, but the cause was still unknown. To understand the issue, we need to understand latency more clearly. Latency is the total time required for a packet to travel across the network, including transmission delay, propagation delay, processing delay inside networking devices, and queuing delay when traffic waits in buffers. For applications like voice over IP, video conferencing, financial transaction, or cloud-hosted systems, even small increases in latency can impact users' experience. Common causes include bandwidth congestion, where links are saturated, routing inefficiencies, where traffic takes a longer than necessary path, hardware performance limitation, such as overloaded routers. And then there's quality of service, which determines how traffic is prioritized when multiple types of data compete for resources. And when QoS is misconfigured, delay can occur even when bandwidth is available. Instead of assuming the problem was congestion, the engineer followed a structured troubleshooting methodology. Step 1. Verify link utilization. Core and edge interfaces were reviewed. Surprisingly, average bandwidth usage was below 60%, well within operational capacity. No traffic spikes, no saturation patterns. Step 2. Check interface statistics. There was no significant packet drops, no CRC errors, no physical layer abnormalities. Step 3. Validate routing path. Traffic was flowing through expected routes with no unusual ops. At this point, the evidence ruled out overload, hardware failure, and routing inefficiency. The network had capacity, yet latency persisted. That shifted the focus away from bandwidth and toward traffic prioritization. Quality of service, or QoS, is designed to ensure critical traffic receives priority during times of contention. In enterprise environments, voice and video traffic are typically assigned to high priority queues. Bulk data transfers, backups, and non-critical services are assigned lower priority. When bandwidth becomes constrained, QoS determines which packets are transmitted first. But if QoS classification rules are misconfigured, traffic can be placed in the wrong queue. In this case, voice traffic, which should have been prioritized, was placed into a lower priority queue. That meant voice packets were waiting behind less critical traffic. Even without congestion, queuing delay was increasing. The engineer reviewed the QoS policy configured in detail. QoS relies on classification rules, match statements that identify traffic based on parameters such as DSCP markings, access control lists, or protocol types. In this configuration, the match statement responsible for identifying voice traffic was incorrect. Because of this misclassification, voice packets were not being marked properly. As a result, they failed to enter the priority queue. That small configuration oversight created a cascading performance issues across applications dependent on real-time communication. One misapt rule: network-wide latency. The solution did not require purchasing new hardware. It did not require increasing bandwidth. It required precision. The engineer corrected the classification rule, ensuring voice traffic was properly identified and marked. Priority queuing was validated. Policy maps were reapplied and verified. Within minutes, latency metrics began stabilizing. Voice calls cleared. Application responsives improved. The network infrastructure had not changed. The configuration had. This case reinforces an important lesson. AI monitoring tools are powerful. They detect anomalies with speed and accuracy. But AI identifies symptoms. Engineers diagnose causes. The AI dashboard correctly detected high latency, but without structured troubleshooting, the team might have assumed congestion and invested in unnecessary upgrades. Instead, analytic thinking prevented wasted resources. Effective network engineering combines automation with human reasoning. As enterprise networks grow more distributed and cloud integrated, AI-driven monitoring becomes essential. However, automation cannot replace architectural understanding. QoS policies, routing strategies, redundancy models, and traffic parasitation require intentional design. Monitoring tools provide visibility. Engineers provide judgment. The most resilient networks are not built by AI alone. They are built by skilled professionals who interpret data correctly and apply disciplined troubleshooting. In today's world, AI can detect anomalies in milliseconds. It can flag latency, predict failures, and analyze patterns across thousands of devices. But technology alone does not build resilient networks. Resilient networks are built by engineers who think critically, who validate assumptions, who look beyond alert. In this case, the AI was correct. Latency was real. But it took human enterprise to uncover the true cause. A simple QoS misconfiguration. No expensive upgrades. No hardware replacement. Just structured troubleshooting and disciplined analysis. This is the future of network engineering. AI detects, engineers decide, and the professional who master both will lead the next generation of infrastructure designs. If you're serious about becoming that engineer, keep learning, keep questioning, and never trust an alert without understanding the why. If you found this breakdown valuable, subscribe for real-world networking engineering scenarios explained clearly and practically. Next week, we analyze packet loss during peak hours and why bandwidth wasn't the problem. Thanks for watching, and I will see you in the next